pleasure to have Megan Reiter visiting us, even though only virtually today. Megan she graduated from University of California, Berkeley, and then she obtained her PhD from the University of Arizona, working with Dr. Nathan Smith. And since obtaining her PhD, she has held the McLaughlin Fellowship at the University of Michigan. And after that, she moved to Europe, where she has a combined fellowship, which is both the Rutherford International and the Marie Curie Fellowship. And for those of you that are not familiar with European Fellowship, Marie Curie is probably one of the best fellowship in Europe, comparable to, very comparable or to the Hubble Fellowship in the US. So she's joining us from the Royal Observatory in Edinburgh in UK, and she will tell us about feedback of massive star, and as you can see from the title, the role of ecology in star and planet formation. As usual, after our talk, we will have an extended Q&A session. So if you have a pressing question for clarification, please use the chat and I will interrupt Megan. Otherwise, please keep your question for the end, and then so we can discuss. So with no further ado, I'll give the control to Megan. So please go ahead.
Can I remind everyone to mute themselves, please?
Thank you, Pat.
All right, great. So thank you very much for that kind introduction. Thank you for the Zoom etiquette reminder. So again, I'm Megan Reiter. I'm talking to you today from my living room here in Edinburgh. And I'm excited to talk with you today about the role of ecology in star and planet formation. And I do mean ecology kind of in the sense that we talk about it biologically, and how we're talking about how organisms interact with their environment. And part of how I got interested in this particular question is because over the course of my career, there's been a real explosion in the number of known extrasolar planets. But as of today, we still know of only one planet that hosts life, and that of course is the Earth. And in many ways, the Earth is still our template for what sort of properties we might be looking for on other planets when we're looking for planets that may themselves host life. So for example, liquid water, which all forms of life seem to depend on, a biochemistry that's built on some of the most abundant elements in the universe. And in particular, the amount of water on the Earth. So while there's quite a bit of surface water, we do actually have dry continents that may be very important for whether or not detectable biosignatures end up in the atmosphere of a planet. Because there's an important difference between a planet that may host life and a planet where we may be able to detect the presence of life through remote sensing. And perhaps dry, rocky continents may be a part of that picture. But I think one of the other big things that we've learned from this explosion of the number of known extrasolar planets is to be cautious about looking to the solar system as our guide for what sort of properties we might be looking for in other planets. So I think that's nicely illustrated by a graph like this one, just looking at the planetary mass here on the y-axis and then the orbital period here on the x-axis, different colors here pointing different detection mechanisms for planets around other stars, and then the planets of the solar system here highlighted. And one of the things that we've learned is the vast majority of planets orbiting other stars don't necessarily look like the planets of the solar system. And part of this is technical, right? It'll be easier to detect a larger planet, and particularly planets that are orbiting closer to their host stars. So something that is smaller and at a wider separation like the Earth is just going to be a lot harder to detect. But there's still a little bit of, say, struggle of models trying to recreate the Earth and solar system in particular, trying to match all of the observed properties in detail. So maybe there's a little bit of a question about how common sort of habitable or Earth-like planets might be. I've always felt a little bit uncomfortable about the suggestion that the Earth might be a little bit unusual in that regard, basically from the Copernican principles. So the history of astronomy carries with it a number of cautions. When we have put the Earth and the solar system at a special place in time and place, we have quickly been humbled. So that starts with Copernicus telling us that the Earth is not the center of the solar system, but then continues when we thought, say, the solar system was at the center of the galaxy, until we understood dust a little bit better and realized there were a lot of stars in one direction we couldn't see. And going further to just about 100 years ago, the Shapley-Curtis debate, trying to understand whether or not the Milky Way galaxy was the extent of the universe, or it was one of many of these sort of spiral nebulae type galaxies in the universe. So my particular approach to this question is not to go out and look for the extrasolar planets themselves. Instead, I want to ask, what's the typical conditions for star and planet formation, and what role does that play in shaping exoplanet demographics in the end? So in many ways, I think our current picture of planet formation is sort of like this incredible image from the ALMA Observatory of H.L. Tau, giving us the incredible structure that you can see in the disks around young stars and the material from which planets are forming, sort of structures in this disk giving us clues about how planets are forming and further observations about chemical interactions and so on and so forth. I would like to argue today that considering the larger star forming environment, it is also an essential part of the picture of planet formation. And in particular, I'm going to focus on three particular ways this can sort of shape the outcome of planet formation. So environmental effects can affect how long planet forming disks survive. So that's going to affect the timescale for planet formation, how long they have to form. Environmental effects can influence the materials available for making planets, the ingredients that might be particularly important for terrestrial planets, Earth-like planets. And finally, I want to think about the star-forming ecosystem as a whole, not only how that's going to regulate these first 2 points, but how that's going to shape the demographics of extrasolar planets as a whole. So stars form in a wide spectrum of masses, but for today, I'm just going to talk in broad terms about low mass stars and high mass stars. So for the purposes of this talk, a low mass star is going to be something about the mass of the sun, maybe a little bit higher. Those are more likely to have Jupiter mass planets than low mass stars, and then certainly some lower mass stars where you're more likely to find sort of Earth-like planets. And particularly important in this case is these stars will live for billions of years. So particularly if we're interested in planets that may ultimately host life, this is going to give you a lot more time for life to develop around these stars. So low mass stars in this case, then in contrast to high mass stars, which will be much shorter lived, so they'll only live for a few million years. So for high mass stars, for me, that's going to be something about 10 times the mass of the sun and higher. So stars that will end their lives as supernova explosions. They also have very strong winds during their lifetimes, this sort of energy and momentum that they inject into their environments, the feedback that Andrea was alluding to in the introduction. And critically, the luminosity of a star goes as something like the mass to the 3/2 power. So what this means is that when you go up, say, a factor of 2 in the mass of your star, you're going to go up more than a factor of 10 in the luminosity of your star. These big stars are incredibly bright. So they're going to have a very big impact, not only on the local environment around the star, the local star formation, but even on the galactic scale. And these high mass stars are going to have a big impact, despite the fact that they're relatively rare. So if we look at the proportion of how stars form for, say, one of these high mass stars, you're still going to end up with about 1,000 of these lower mass stars. And one of the reasons we'd want to then think about these kinds of environments where you have high mass stars and low mass stars living together is because observations indicate a cluster mass function that goes as something like n to the -2 power. And what this means is that at least half of all the stars in the universe are forming alongside high mass stars in high mass star forming regions like the Orion Nebula. And we can see some of the immediate impacts that the presence of high mass stars are going to have on the star formation in beautiful images like this one from the Hubble Space Telescope that are beautiful in part because these high mass stars are lighting up the gas in the star forming region, creating these beautiful nebular images. The radiation from these stars may also be affecting other stars in the environment. I'm not going to talk too much about that today. There's not much evidence that this will, say, change the initial mass function, but we're certainly looking into whether or not this might affect, say, the fraction of stars that are born in binary pairs. So this is work led by a graduate student at the University of Michigan that I've been working with, Matthew DeFurio. If you're interested in the binary demographics in Orion that we've been working on, I encourage you to look at Matthew's 2019 paper. I think the other thing this incredible Hubble Space Telescope image shows us, though, about how the high mass stars are infecting the environment is in these postage stamp images here of planet-forming disks around low mass stars that are clearly being lit up by the nearby high mass stars. So they're not only being illuminated, but they're being evaporated, quickly sort of planet-forming material being boiled off of these planet-forming disks around the low mass stars in this environment. So we can see that in these postage stamp images. We can see that, say, with ALMA surveys looking at the cold gas and dust most closely associated with planet formation in the disks in this region. So disks in the Orion region here are shown in this red line. And what this paper found was that overall these disks are smaller in physical size and lighter in their mass, compared to, say, the disks that you find in nearby star-forming regions that don't necessarily have a high-mass star kicking around. So I'm going to highlight here just the Taurus star-forming region as sort of another local region where we're often looking at star-forming studies. So when we're talking about how the larger environment is affecting the star and planet, particularly the planet formation, we're usually talking about two key physical mechanisms, and that's going to be dynamical interactions between the stars and their disks in the region, or the influence of that external radiation that's evaporating the disks around nearby low mass stars. So if we sort of think about how these two things might operate in a region, I would look to a paper from Andrew Winter in 2018 that kind of looked at these two effects. So on the x-axis here, we're just looking at the density of the star-forming region. And on the y-axis here, we're looking at the ionizing radiation in the region. So the argument from this particular paper was that when you're above a certain density, you'll have significant tidal truncation of planet-forming disks of a certain size over about 3 million years. And then the argument is that above a certain level of radiation, you'll have a significant destruction of planet-forming disks, again, of a certain size over 3 million years because of that external radiation from the high mass stars. So just to highlight a couple of points on this graph that are related to famous high mass star forming regions, say the Orion Nebula cluster, Templar 14 in the Carina Nebula, or the Cygnus OB2 star forming regions, you can see that even within a single region, you're going to have a range of different conditions. But one of the arguments of this paper is that, for any density, you will reach the point where external radiation from other stars in the environment are going to lead to significant disk destruction before you even get to the higher densities where tidal interactions between stars becomes important. So radiation from other stars in the environment is a significant, mechanism for disk destruction, particularly in these high mass regions. So the thing that I would add to a plot like this is just to highlight the fact that star-forming regions evolve with time. There'll be dynamical evolutions in the regions, which means that their density will change with time. So for example, if we're thinking about cool collapse models where stars are falling in to build up a cluster of stars, the density will be growing with time. And in contrast, while many of these stars are forming in clusters in the statistical sense, in that stars are forming near other stars, most stars are not forming in gravitationally bound systems where if we come back, say, in 1 billion years, it'll still look like a bound system of stars, which means that at some point the density must be decreasing with time in these systems. I would argue we also want to understand this full parameter space if we want to understand the diversity of planet-forming environments. For example, recent work from Nick Wright on the Cygnus OB2 star forming region has argued that it's always been a low density association. So in contrast to some models that would suggest that these clusters started at high density in the past, and then we're seeing them now at a later time when they've dispersed, the argument from these papers was that the star forming region's always been a low density. On the other extreme here, highlighting kind of higher density regions, I would argue that these star forming conditions are much closer to typical star forming conditions near the peak of cosmic star formation. Now, this is not something that we talk about very often when we're talking about planet formation, but I would argue that we should be. In particular, most of the extrasolar planets that we're finding now are around stars that are a few billion years old. So if we want to understand the typical star forming conditions at the time that these planetary systems were formed, we want to be looking at conditions that are more similar to earlier epochs of star formation earlier in the universe. This is particularly true also given that one of our best indicators of the composition of extrasolar planets is extrasolar asteroids crashing into white dwarfs. So at the point that we're probing the stellar graveyard, we certainly need to think about what kind of star forming conditions would have been representative at the time that these systems formed. So to add this kind of dynamic piece to the puzzle here about how different mechanisms are affecting planet forming disks, I wanted to take the observational perspective, and to do this, to go to one of my favorite high mass star forming regions, the Carina Nebula. So there are a couple of advantages to this, not the least of which we have two sort of high mass clusters right next to each other in this region. So that's Trempler 14 on the right and Trempler 16 on the left. These brightly colored points are X-ray detections of low mass stars in the regions. Again, it's a high mass star forming region so that we have many, many high mass stars kicking around in both clusters. Those are the blue stars up on this image. So to try and add the kinematic piece, the first thing that we want to do is make sure we're looking at dynamically young systems so that we can then start comparing to numerical models to try and trace how the dynamical evolution of the region actually affects how long the disks survive. So Richard Parker and I went and did this to do a structural analysis of the regions to decide or determine whether or not they're dynamically young. So we're looking for things like evidence of mass segregation. Are your high mass stars more concentrated towards the center of the cluster? Are the distribution of stars relatively smoothly radially distributed? And in both of these cases, we found they're not particularly mass segregated. They're not particularly smooth distributions. They're both dynamically young regions, good targets for a kinematic study. Now, we're currently living in an era with the Gaia astrometric satellite providing motions of an incredible number of stars in the galaxy. Unfortunately, though, if you're interested in looking at low mass stars in a truly high mass star forming region, the stars end up being a little bit too faint to get a good proper motion measurement from the Gaia astrometric mission. So instead we need to use other techniques. Now, fortunately for a region like Carina, which is basically in the next spiral arm over in the galaxy, there's not too much intervening material. It's possible to use multi-object spectrographs to obtain optical spectra of many of these stars using some of the larger telescopes available today. So I'm leading a radial velocity survey trying to target, again, a large quantity of the low mass stars in these regions. I'm just showing here a quick reduction of the first epoch of this survey. Observations are ongoing. I had a few nights earlier this year. Thankfully, telescopes are beginning to resume operations. So again, this is just a quick reduction, but if you'll join me in a little bit of science by squinting, we can just note, say, the velocities of the Trempler 16 cluster, shown here on the left in red, and Trempler 14, shown here on the right in black, are remarkably similar, despite the differences in their apparent morphology. So one of the things that we want to do with this larger radial velocity survey is get a good kinematic constraint on these low mass stars because they're most likely to host terrestrial planets, low mass stars because they're so numerous, they're going to dominate the mass of the cluster. So if we combine this kinematic study with this sort of structural analysis together, that's going to allow us to break degeneracies in the dynamical history of the region and make a more direct comparison between numerical models of how star forming regions evolve and the data here, with a goal to understanding how the motion of stars in their star forming environments determines their disk lifetime. So we can make a first estimate with just the structural analysis alone, and Richard Parker and I did so, by comparing the structure of the regions to the surviving disk fractions. And for this, we use near-infrared excess emission as measured by Thomas Breibisch. So this is going to be tracing warm dust and remaining circumstellar disks. And the thing is, the remaining disk fractions in these two clusters is relatively small. It's 10% or less in both cases. But that's about what you would expect for two clusters of slightly different densities dynamically evolving, especially if Trumpler 16 is slightly older than Trumpler 14, as its evolved star content would suggest. So I think it would be easy to look at these relatively low disk fractions in relatively young clusters and think that perhaps high mass star forming regions are pretty inhospitable for planet formation. Now that would be a little bit at odds with the observation or the estimate of the fraction of low mass stars that host planets, which I think is something on the order of all of them. So the other thing then that this would imply is that planet formation has to be fast. And to better quantify fast, we'll need the kinematic study to do that. The other reason to be targeting these high mass star forming regions and trying to understand the planet formation in these surviving disks is to understand what ingredients are available to make the planets in them. And in particular, there are a few elements that appear to be important, not only for the chemistry of the planets, but possibly the water budget of the Earth-like planets that are forming in these regions. And the water budget in particular, meaning not too much water. So while the Earth has quite a bit of surface water, in terms of its bulk composition, it's really not that much water. Earth is a relatively dry planet. And the argument is that short-lived radioactive elements that are synthesized in the death of high mass stars might be a very important piece of regulating just how much water Earth-like planets have. So this is a model from Tim Lichtenberg that came out in 2019, and the picture is this. If a system has as much of this short-lived radioactive element, 26 aluminum, if it has as much or more than was detected or inferred for the early solar system for the formation of the Earth, what happens is when that radioactively decays, the half-life of 26 aluminum is about 0.7 million years, you'll get an extra heat source. And what this does is dehydrate your planetesimals. And the resulting planet that is built up from these dehydrated planetesimals will be a drier and rockier and more Earth-like extrasolar planet. The contrasting scenario, of course, is if you have much less 26 aluminum than was inferred for the early solar system, you don't get this extra heat source. And as a result, you'll have more water-rich, more volatile-rich planetesimals, leading to a much more water-rich final planet. So either water world, something engulfed in ices. And as I think this press release image nicely demonstrates, likely a larger planetary radius. So one of the challenges for explaining the presence of 26 aluminum in the solar system, and then that would extend to other planetary systems with 26 aluminum enrichment, is the fact that it's a short-lived radioactive isotope, which means that if you want to get the 26 aluminum into the system before it radioactively decays, you must be forming your planetary system relatively close in space and time to a production source of 26 aluminum. On the other hand, if you're really interested in high mass stars and their role in driving the chemical evolution of the galaxy and some of the broader feedback questions, 26 aluminum is great because it's a short-lived radioactive element, which means that where you see it in the galaxy, it must be close to one of its production sources. So we flew a couple of gamma ray satellites, I believe in the 90s, in pursuit of exactly this question. And we're able to produce all sky maps of the gamma ray emission line that is produced from the radioactive decay of 26 aluminum. And looking at this all sky map of the 26 aluminum in the galaxy, I think a couple of things are immediately obvious. It's mostly confined to the plane of the galaxy, and it's particularly bright in some famous high mass star forming regions, regions like Cygnus, regions like Carina, and regions like Orion. So I argued in a paper last year that if 26 aluminum is really as important for planetary composition as the models of Tim Lichtenberg would suggest, what this immediately implies is that some environments are going to be more conducive to forming Earth-like planets than others. So we can think about that sort of in the specific example, again, of the Carina Nebula. We're looking here at a larger scale image, encompassing the entire star forming complex. So just a moment ago, we were looking only at the two central clusters. So Carina is a much larger star forming region. And we want to take this zoomed out view because that's about everything that's contained within the resolution element of these gamma ray observations. So we don't have a great deal of information about how this 26 aluminum is distributed in the star forming region. But we can certainly ask the question, how much 26 aluminum is there, and how much cold gas and dust, how much of the raw materials for star formation are contained in this region? So doing that quick calculation, it turns out that the current abundance of 26 aluminum in the Carina star forming region is about the same order of magnitude as what we infer for the early solar system. So very favorable perhaps to forming rocky and Earth-like planets. And this is perhaps particularly noteworthy because the Carina star forming complex is still relatively young. The vast majority of the high mass stars have not yet exploded as supernovae. So I think this points to a real opportunity in terms of trying to understand how the star forming environment is affecting planet composition by looking at sort of the complement between what the high mass star community has looked at in terms of the production of 26 aluminum and what that might mean for planet formation. So one specific example, again, looking at Carina, if we're thinking not just about an individual star that might produce 26 aluminum, but we're thinking about this entire ecosystem using the fact that we know something about the population of high mass stars, you can go and say do population synthesis modeling to try and understand the production of 26 aluminum. And you can match that to the current observation. That's the dotted line here in the middle of this plot. But one of the things that I think is particularly interesting about this population synthesis study is then the estimates of how that stellar population, how much 26 aluminum it will be producing as a function of time. So for example, we can see in the next few million years, we expect there to be an increase in the amount of 26 aluminum in the region as more and more of those high mass stars explode as supernovae. But I think the other particularly striking thing is just how broad this distribution is. So again, the current abundance of 26 aluminum is about on the order of what we expect for the early solar system. And what this modeling suggests is that that has been true for at least 5 million years, and it will be at that level, if not higher, for another 5 million years. So when we consider an entire ecosystem a collection of stars, this would suggest that this short-lived element could be abundant in the region for millions of years. This is much longer than the 0.7 million year half-life that you would expect for any one production event. So I think it would be wrong to say that having this element around for millions of years means that everything gets enriched. But I think having this element around for millions of years certainly changes the number of systems that are exposed. And I've argued that could be an order of magnitude difference. And I think there are questions to be asked here using, in particular, what we've learned about high mass stars in the decades since this work was done to really re-examine exactly how wide this distribution is, to understand how long the 26 aluminum is around, to better estimate what fraction of systems are enriched and what fraction might be forming Earth-like planets. So that's a lot of discussion about low mass stars as sort of disk-bearing sources, about high mass stars as drivers of the chemistry in the region. But if we're thinking about the ecosystem, we also have to consider the fact that they tend to have a lot of gas and dust around. So if we go back to the central clusters of the Carina Nebula, but this time looking at the color image, revealing just how much gas and dust is still around in Carina. So again, we've got Trempler 14 on the right here and Trempler 16 on the left. And a lot of ionized gas around, a lot of cold gas and dust, the sort of raw materials of star formation kind of at the edges of this particular image. We can start asking, how does the gas and dust in the region affect both of these questions? So for example, gas and dust will have its own mass, can affect the dynamical evolution of the clusters. The gas is also absorbing ionizing radiation. That's part of why this is a spectacular image. Does that help protect disks? But the question is, so where do we go to start testing what the gas and dust are doing? So we might want to say repeat the experiment done looking at some of the irradiated disks in Orion and go look with ALMA, try and measure the cold gas and dust associated with any remaining disks in something like Trempler 14. Unfortunately, efforts to do this so far haven't detected any cold dust emission from these disks. For the interested reader, the upper limits there are about 7 Jupiter masses. But nevertheless, there's been no detection of cold dust with any of these exposed disks in the H2 region. So there are plenty of clouds sort of around here, evidence that there might be other stars forming. And it would certainly be interesting to go look and target those systems that are still embedded in their star forming cocoon, particularly to understand how that remaining material is helping perhaps protect those disks. But there's a little bit of a problem. In part, the question is, where do you look? So we've got a little bit of a mismatch. If you're looking for survey power to look at a large portion of this region and detect, kind of just understand what's around, the best single dish observatories, the best sort of survey facilities have pretty coarse resolution, especially at these distances. So I tried to eyeball the typical resolution element of say a millimeter observatory that you would get. And I think putting that on top of this incredible HST image highlights the problem. You can get quite a bit of stuff into that resolution element, and you're going to be dominated by the brightest thing. Now, fortunately, we have the ALMA observatory, which can provide angular resolution that's comparable to what you get with the Hubble Space Telescope. But then the question becomes, where do you point? Because again, you can't necessarily go out and survey things. So I would argue this requires us to be a little bit more clever and approach this slightly differently than we have in some of the nearby star forming regions. We can use what we know about how stars form. So for example, as I imagine a department with Pat Hartigan in it would know, protostellar jets are part of the star forming process. So when stars are forming, material is collapsing into a disk that's feeding material onto the star. And as part of that process, some fraction of that material gets shot out in these protostellar jets. So these can make for spectacular images, in part because they extend so far on the sky. So they're going to extend much, much larger scales than the disk themselves, creating a pretty good signpost of ongoing star formation, of ongoing disk accretion. So we can use something like imaging, particularly in a region like the Carina Nebula, where you have all of these high mass stars around, lighting up absolutely everything, including the protostellar jets, to go looking for signs that there are young disk systems around. So this was actually my PhD thesis, going and looking at many jets in this particular region. And so we were looking with multi-wavelength imaging, trying to constrain the properties of the jets, trying to constrain the kinematics of the jets, wanting to understand a lot about how the stars themselves are forming, but also producing a pretty well-constrained set of sources where we have a very good idea exactly where you think a young star-forming system would be, what kind of inclination you have on the system, so you have an idea about how you think your disk would be oriented, and a very good idea about where you should be pointing ALMA if you want to be looking at disks around relatively low mass stars in these kinds of high mass star forming regions. So I was very excited that Mesa Delgado et al. Went and did exactly this with one of the longer baseline campaigns with ALMA. So we're looking at the dust continuum emission in this color scale image on the bottom. And I will note that the size of that is not that much larger than the beam size. So this is a barely resolved bit of dust around a young star. But nevertheless, we can be relatively confident that what we're looking at here is indeed a disk, because again, we have a pretty good idea what we're looking at. We know kind of what inclination we're dealing with because of the jet. So this is the kind of roadmap for what I want to do, understanding not only the disks around stars, but understanding the disks in the context of their ecosystem. So for that, I'm looking at an example on the other side of Carina here, next to the Trumpler 16 star cluster. And sort of a similar setup. We can see this bright jet coming out of this little star forming globule. The jet is very bright. It's lit up by all of these high mass stars nearby in Trumpler 16. We've taken to calling this little system the tadpole, because you'll note this little star forming globule's got this weird head and this kind of weird wiggly tail. For obvious morphological reasons, it looks a bit like an actual tadpole. We found out around paper 2 that there's actually a different star forming region called the tadpole. So that is an unfortunate naming duplicate. That was my bad. But as a sort of star forming example, the tadpole then is a place for us to look not only at the star forming disk, but what this sort of star forming cocoon is doing to help or hinder the star and planet forming system. So to start, we want to actually quantify how much those nearby high mass stars are actually affecting this system. And to do that, we obtained Mu's integral field unit spectroscopy. So what that is this is not only an image, but it's a spectrum at every point of the image, giving us a wide variety of spectral diagnostics to try and measure the physical conditions in the ionized gas in the system. So for example, I could go in and not only know that I have ionizing radiation coming in from Templar-16, but then quantify what's happening by measuring the density in the gas and the temperature and the ionization fraction. So I can do this over the entire image, but I'm just going to show here a slice across the globule of how some of these physical properties change over the system. So again, we can look at the density of the gas, we can look at the temperature, we can look at the ionization and see how they're changing over the entire image, but certainly over the system. And this allows us to calculate a variety of different physical properties about the system, including how fast those nearby high mass stars are boiling material off of the system. How fast is this being evaporated by its environment? And it turns out, if we assume that the mass of this system is about 1 to 2 solar masses, it's actually not that fast, relatively speaking. At the rate that we estimate that the high mass stars are evaporating this globule, it will survive for another 4 million years or so, which is actually relatively long compared to the time that we think it takes planets to form. So it's not clear if the star and planet forming system embedded in this globule really cares about the harsh environment that it lives in. But to test that, what we really want to do is look inside the globule and look at the cold and gas and dust associated with planet formation. And for that, we need ALMA, which can, again, provide the angular resolution comparable to what you can get with the Hubble Space Telescope. So showing here just some contours of the molecular gas emission plotted on top of that Hubble Space Telescope image. So what we want to do then with this ALMA observations, again, is to peer into the tadpole and try and measure how much that embedded star and planet forming system cares about its environment. So the presence of the ionization front on the globule, the ionized gas around, would certainly suggest that this is living in a hot environment. And in fact, we see that when we look more closely at the ALMA data. So one of the things that quickly stands out when we look at the molecular gas here is this beautiful molecular outflow. So we can see the blue shifted side and the red shifted side here inside the globule. But you'll note that they end exactly at the end of the globule. Outside of the protection of this globule, it's simply too hot for the molecules to survive. Now, I have to admit, I was pretty excited to see this because this is very much inside the globule what you would expect to see in a relatively quiescent nearby environment. And as soon as you're outside of that globule, the jet gets lit up, kind of illustrating exactly what you would expect if this is the same kind of outflow physics that you get locally, but basically with better stage lighting. What this also means is that while it's relatively hot outside the globule, it's too hot for molecules to survive, it's still cool enough inside the globule for the molecules to survive and trace this beautiful molecular outflow. We have a few other lines of evidence suggesting that this there's a temperature structure in the globule itself. For example, if we look at the brightness temperature of the gas, so if you have an optically thick line like carbon monoxide here, the brightness of that line will be related to the temperature of the gas. And with these well-resolved observations of this tadpole globule, we can actually look at the variation in the brightness of the line and the temperature of the gas over the surface of the globule. And one of the things that this suggests is that the surface of the globule is actually hotter than the center of the globule. So we're looking at a positive radial temperature gradient, something that suggests that the gas is being heated externally, perhaps by that cluster of high mass stars just beyond the globule. So there are a few lines of evidence that suggest that while the globule is hot on the surface, it actually is still relatively cool in the center of the globule. So for example, if we go and look at the dust emission around the protostar, so in this image here, that's going to be the black and gray contours. I'll note that that is intriguingly flattened, but I will not be so bold to call that a disk. When we try to model this dust continuum emission of the material around this protostar, we don't get a very good fit with models that have too warm a temperature. The best fitting models require a temperature of about 15 Kelvin, require pretty cold dust to match the observations. And in particular, they also require some evidence for grain growth, some sign that planet formation is already ongoing in this dust. We have an additional piece of evidence that the gas and dust nearest this protostar is cold from the chemistry in the gas. So we quite accidentally detected DCN. So that's the color scale that we're looking at here on the right. And again, the contours are tracing the dust continuum emission. And I've just put some outflow contours on here to guide the eye. So we detected a deuterated molecule very near the star forming system. And what this is telling us is that the gas must be cold. Chemical reactions that favor the production of deuterated molecules are much more likely in the colder gas. And in this case, particularly gas that is cold enough that the carbon monoxide is frozen out of the gas phase. So where you see the deuterated molecules suggests that either the gas is cold or that it was cold in the recent past. So taken together, there's evidence that the globule is hotter on the surface, but the gas and dust inside must be cold, suggesting that this star and planet forming system might be evolving just fine and blissfully unaware of the messy environment that it lives in. So the final thing that we'd want to look at is the kinematics of the globule. So not only do we get incredible angular resolution with the AMA observatory, we also get excellent spectral resolution. So this is typically done by looking at the shape of line profiles, in particular characteristic asymmetries that will tell you something about how the gas is moving. I'm not going to say too much about that for no other reason than the line profiles in this particular globule are stubbornly centrally peaked and not very telling in that regard. But the other thing that we can do is use the fact that this is a spatially resolved source and look at the velocity of the gas as a function of position across the gas. So to do that, I'm going to take a slice across the source perpendicular to that incredible outflow, so it has a minimal impact on the kinematics of the gas that we're measuring. And what we get is something like this, which looks like it's straight out of Star Trek, but it's this kind of peculiar C-shaped velocity feature. Now, some folks have argued that this kind of C-shaped feature might be indicative of inflowing gas in high mass star forming regions. I was scratching my head about this and approached my colleague, Tom Haworth, who has models of inflowing gas and outflowing gas that in broad brush strokes can reproduce this sort of C-shaped morphology. But we have yet to come up with a model that can reproduce this peculiar C shape in detail. So what's happening with this globule kinematically is a bit of a mystery. So it's not obvious, say, that the impact of the environment is actually acting to compress the globule, forcing it to be collapsing faster, or some other thing that a distinctive infall signature would suggest.
Megan, can I ask you a question about this velocity position diagram? What
Yes.
What is the systemic velocity?
So the systemic velocity, this is a great question, is about 32.5. That is to say, the reddest of the velocities on this system.
Okay, thank you.
Yeah, I think, yeah, part of the reason we were also looking at the outflow question. Are there any other questions before I plow on? Okay. So that was sort of a whirlwind tour then of the tadpole globule, but I think it's a really nice example of what we want to do on a much larger scale. And that is to say, look at a variety of different high mass star forming regions or high mass star feedback on a variety of different realistic cloud interfaces, understand what that's doing, what sort of feedback is hitting the gas and what the consequences are for the cold molecular gas most closely associated with star and planet formation. And I would argue, I am part of a ongoing collaboration doing this for different parts and star forming pillars in the Carina Nebula. But I think one of the things that we really want to do is trying to do this on a much larger scale to get an idea of a scaling relationship between how the incident ionizing radiation affects the gas and what the consequences are. And for that, I think M17, shown here on the left, is a really great target. It's a young region. The central cluster of stars in M17 is actually pretty similar to Trumpler 14 in the Carina Nebula. It's relatively young, the gas is nearby, making a nice comparison set. and making a nice, bright, illuminated, well-oriented interface to try and understand, again, this connection between how the high mass stars are affecting the ongoing star and planet formation. M17 happens to be accidentally a beautiful morphological match for what we think that might do to the gas kinematically, shown in this simulation from Jim Dale. So the plan is to do for M17 much like we did with the tadpole-shaped globule. So to go and map a large portion of this ionized interface in the M17 star-forming region with MUSE, again, getting a spectrum of every point of the image to get a number of diagnostics of the ionized gas and understand exactly what the impact of those high mass stars is on the gas. And then go look at more or less the same region with ALMA to try and understand what the consequences are of that as for the cold molecular gas and dust most associated with star formation. So I'm very pleased to say that both of these programs have been awarded. Observations are ongoing, or at least will be, pandemic permitting, soon, providing not only a large data set to be looking at how the high mass stars are affecting sort of the gas interface and the sources within it, but also providing presumably a large number of sort of analogs to this tadpole system. Individual star and planet forming systems, we will have a very good idea how the environment is impacting them. We will have quantified that impact and we'll know exactly where we want to go to look to be chasing down what that means for these systems in terms of their chemistry and their kinematics. And I would argue that this is a great time to be doing these kinds of investigations because we're looking at a future where that's exactly the kind of study that's going to be possible with these larger aperture infrared optimized observatories. So hopefully later this year, we will see the launch of the James Webb Space Telescope. Hopefully later this decade, we will see the first observations from the 30-meter class telescopes coming online. My particular interest is for the giant Magellan telescope going into Chile. And in both of these cases, providing the large collecting area that you need to start chasing down the chemistry and kinematics of individual star and planet forming systems in these kind of more intense high mass star forming regions, the many tadpole analogs that we hope to be finding in a region like M17, and chasing down this connection between how a variety of feedback from these high mass stars is affecting star forming gas and dust, and taking that from quantifying its impact on the gas and what that means in terms of the chemistry and kinematics of the star-forming gas. We looked at the specific example of this little tadpole globule and saw that there's clear evidence that the environment is absolutely affecting the tadpole. It's hotter on the surface. We can see this ionized jet. But in terms of the star and planet forming system embedded in the middle, it seems relatively unaware of its intense environment. The gas and dust is cold. There's evidence for grain growth. And by our best estimates, it will be a few million years before the system is exposed to the really intense radiation of this high mass star forming region. And we know that this kind of protection from the star forming cocoon might be very important because once those disks are exposed in the high mass star forming region, they're pretty quickly destroyed, leaving not too much time for planet formation. So I hope in this whirlwind tour of high mass star forming regions, I've convinced you that there really is a place for considering the star forming environment in the picture of planet formation, in particular looking at these three themes. So with that, I will put up my conclusions. I thank you very much for your attention, and I'm very happy to take any further questions.
Thank you, Megan. I'm gonna clap for everybody. Thank you very